Today we're going to look at graphing trig functions. So we've already seen graphs of sine and graphs of cosine when we were talking about transformations of parent functions, but we're going to take a closer look at to where the graph of sine comes from, where the graph of cosine comes from, and their specific names for their transformations and how they kind of move about the coordinate grid. So the first thing I want to do is let's just look at the graph of sine. So if we're looking at the graph of sine, I'm going to draw in my x-axis. I'm going to draw in my y-axis. And you probably already noticed that my coordinate grid isn't square like we normally work with. It's a little bit more rectangular, it's longer. And I did that on purpose because when I'm working with sine and cosine, I don't want to just count 1, 2, 3, 4 like I normally do, because the numbers that I'm used to working with for sine and cosine are 0, pi over 6, pi over 4, pi over 3. So I want to count by numbers that are actually useful to me, not numbers that aren't so useful. So to make it as straightforward and as simple to graph as possible, I'm going to use my radian values of 0, pi over 2, pi, 3 pi over 2, and then when we get back to 0, we know that's also 2 pi. And the reason I'm going to use those is because if I look at those coordinates, I have the coordinates 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Personally, I'd prefer to graph numbers like 0 and 1 versus trying to graph something like the square root of 3 over 2. So I'm intentionally going to pick those points. I'm going to plot those points, connect the dots to get my picture. So when I look at this, if I have the sine of 0, I know when I'm finding sine values, I'm looking at the y coordinate. So I'm really just concerned with my y coordinates. So 0, 1, 0, negative 1. So at 0, the sine of 0 is 0. So that means the first point I can plot on my graph is 0, 0. Then, when I get to pi over 2, now, like I said before, I don't want to count 1, 2, 3, 4, because then I have to plug in numbers like the sine of 1. I don't know the sine of 1. The sine of 2, I don't know that off the top of my head. I'm going to count by numbers that make it easy for me to plot this. So I'm intentionally going to count by pi over 2, pi, 3 pi over 2, 2 pi. I'm going to count by the numbers on my unit circle so that when I'm plotting these points, it's easy for me to pick out the values. So when I find the sine of pi over 2, I see that it's 1. So it's okay for me to count here by ones. I'm going to go up 1. Then the sine of pi is 0, so I'm back here. The sine of 3 pi over 2 is negative 1. The sine of 2 pi is 0. And if I kept going, which I know I can, if I kept traveling around my unit circle, I see that that pattern is just going to keep repeating. I'm going to go back up to 1, then 0, down to negative 1, 0, 1, 0. And no matter how many times I travel around the unit circle, I can just keep creating this graph that runs through here forever. If I travel backwards, all that happens is my pattern is reversed. So now I'm going to go down to negative 1, 0, back up to 1, 0, negative 1, 0, 1, 0, negative 1, and same thing, that'll keep happening forever and ever. So I can use the unit circle in order to get myself a picture of the sine graph if I forget what the sine graph looks like. So what we're going to do today is we're going to take sine, we're going to take cosine, and we're going to transform them and be able to graph them and identify the pieces of their functions. So before we do that, let's just build a graph of cosine so that we can really make sure we have a good understanding of this. Let me just move this so it's a little bit more. All right. So I'm going to draw my x-axis and my y-axis. And again, I want to count by pi over 2. Then I would have pi, 3 pi over 2, 2 pi, and so on. Backwards, I would have negative pi over 2, negative 3 pi over 2. Wasn't going to be able to fit all of it. Negative 5 pi over 2, and so on. So if I'm going to graph cosine of 0, the cosine of 0 is my x value at 0, which is just 1. So when I plot the cosine of 0, I'm starting at 1. The cosine of pi over 2 is 0. The cosine of pi is negative 1. The cosine of 3 pi over 2 is 0. The cosine of 2 pi is 1. And I can already see my pattern now repeating, so I can fill in the rest of my pattern for the rest of my graph. And this would go on forever and ever if we wanted to, because we know that we can travel around the unit circle as many times as we want. And then we have our picture of the cosine graph. So let's look a little bit more at how we're going to move this graph around. So first, let's look at the amplitude of the graph. And the amplitude of the graph is just how tall the graph is. How tall the graph is. When we were talking about transformations earlier in the year, our transformation that is equivalent to amplitude is just the vertical stretch or shrink of the graph. Here we're just going to talk about it as amplitude, since we see that the sine and cosine graphs oscillate or they repeat over and over again. We use different words to describe it because it's a repeating graph, it's an oscillating graph. So when we're talking about how much we stretch the graph vertically or shrunk the graph vertically, we refer to it as amplitude. So this is, mathematically, it looks the same as our vertical stretch and shrink. We just have a different name for it because it's specifically dealing with sine and cosine graphs. So when we're looking for the amplitude in the equation, the amplitude is always going to be this first variable that we're multiplying the sine or cosine function by. And it follows those same rules where if we multiply by a whole number, it's going to make the amplitude bigger. If we multiply by a fraction, it's going to make the amplitude smaller. If we're looking at an actual picture to kind of get an understanding of what amplitude is, if we bring up the sine graph, which we know starts at the origin and kind of just oscillates back and forth like this, the amplitude is how high each piece of the graph is from its center. So this is the amplitude. So our standard parent function for sine and cosine have an amplitude of 1 because they're just up 1 point, down 1 point. So it's how big or how far away from that is from the middle. So let's look at some graphs that don't necessarily have an amplitude of 1 and what happens when they don't have an amplitude of 1. So if we look at this first one, the graph of f of x equals 2 sine of x, we see that we have an amplitude of 2 here. And what's going to happen when we graph this So we're going to take our parent function of sine, and it's going to get taller by a factor of 2. So if I just draw in my original sine function, which I know starts at the origin, goes up 1, back down, down. Here's my regular sine function, and I always like to draw in my parent function and then just transform my parent function rather than trying to do it all in my head. So here is my parent function. I'm going to take each one of these points, and instead of being up 1, now they're going to be up 2. It's going to have an amplitude of 2. So anything that was on the y-axis is going to stay on the y-axis because it's still my center of my graph. It's 0. If I multiply 0 by 2, nothing happens. But when I multiply 1 by 2, I get 2. When I multiply -1 by 2, I get -2. So my graph is just getting taller by a factor of 2 because I have an amplitude of 2. So my new graph just looks like I stretched it and made each piece taller. So now the next one, I have an amplitude of 1/2, and I know that because that's the number out in front. So amplitude equals 1/2. When I'm graphing this, same thing, it's a cosine graph, so I'm going to draw in my cosine function, and then I'm going to transform it to get my new function. So cosine, I know, starts up at 1, and then goes to 0, -1. So I'm just going to draw in my pattern for my cosine function so that I have these points to transform. Duke is very excited about this one. He wanted to make sure you all knew how exciting it was. He's telling the neighbors too how exciting it is. So now that I have my cosine function, I just want to take each of those points and I want my amplitude to be 1/2 of what it was originally. So my points that are on the y or on the x-axis are going to stay on the x-axis because they have y values of 0. So when I multiply 0 by 1/2, nothing happens. But all of my other points are going to shrink down to be 1/2. So then I'm going to 0, -1/2, 0, 1/2. My amplitude is shrinking to be 1/2. So this is taking my graph and bringing it closer to the x-axis. Then I'm just going to finish up my pattern all the way across so that I can fill in my graph. So the amplitude is just our fancy trig word for vertical stretch or shrink. The next one we have is a phase shift. So a phase shift is very similar. It's going to move our graph left or right. The thing that's tricky about it is because we saw our graphs just repeat over and over and over again, it's hard to see how much they moved necessarily because the pattern is continuing. So we call this a phase shift because we're going to take that phase of the graph and we're going to move it over to the left or the right. So this is still going to move left or right. It's still going to be that number inside the parentheses with the x, and it's also still going to be a negative c will move right, a positive c moves left. The thing that's going to be the most alarming is when we look at these graphs, because our x-axis is now scaled by pi over 2, most of these values will always be radian numbers. So they're going to be things like pi over 2 or pi over 4. We want them to be like that. So even though when you first see the equation, it's going to look a little more alarming because now you're going to have 3 pi over 2 in there instead of just a 7. It's okay because we want it to be like that. That's how we scaled our x-axis, so that allows us to shift it left and right easier. So if we look at this first example, we have f of x equals sine of x minus pi over 2. So this is the pi over 2 that I was talking about. It looks a little scary. We're used to seeing whole numbers in there, but it's okay because moving pi over 2 is easier for us when we've got our x-axis scaled like that. So here we can say our phase shift is going to be to the right since it's negative, right, and pi over 2. So we're going to move every point to the right pi over 2. So first let's go in and draw our x-axis and draw our y-axis. And then let's go in and label. So just to make this a little bit easier for us to see, I'm going to count by blocks of 2. So this will be pi over 2. This will be pi, just so I can space it out a little bit more for you to be able to see. 3 pi over 2. 2 pi. Negative pi over 2. Negative pi. Negative 3 pi over 2. Negative 2 pi. And now I can still count by ones. That's fine. I just wanted to be able to write in those radian values for you without having to totally squish them so you could easily see them. Okay, so when I draw my regular sine function, I know my sine function starts at 0, 0, goes up 1, down to 0, down 1, up 1, down to 0, back and forth. Oop. There we go. So that's my just regular sine of x. But now I want to take that entire graph and I want to move it to the right pi over 2. So that means every single point on my graph is going to move right pi over 2. So the point that was here is now moving here. So I'm going to take each point and move it forward pi over 2. So my origin moves to pi over 2. This point moves over to pi. This point moves over to 3 pi over 2. Moving over. And so on. I may run out of room. That's okay because I have my pattern. So now once you've kind of gotten your pattern, you can continue to just move all of the points over. Or if you kind of see your pattern, you can just go in and finish it off. It's up to you, as long as you know where the graph is going to be. So now the blue one is our sine of x minus pi over 2. That's our shifted graph. So when we're shifting these graphs, we're just moving them left or right. We're calling it a phase shift though because we're taking each piece of the graph, each phase of the graph that's oscillating back and forth, and we're shifting it over. So then if we look at the next one, cosine of x plus pi, our phase shift is going to be left because it's positive. Left pi. So let's go in first, draw on our cosine graph, and then we can transform it. So I'm going to do the same thing here. I'm going to scale by 2 on my x-axis just so I have room. Use that same scale as before. That gave me more room to show my work. Okay. So my cosine graph, we know, starts up at 1, then comes down to 0, -1, 0, 1, goes down. All right. So now that I have my cosine graph, cosine of x, I want to take that graph and I want to move every point to the left pi. So I like to start at the origin. And I take that point right here and I'm going to move it to the left until I get to pi. So that means that point is coming here. My next point is going to the left pi. So it's going to be here. Now I'm at this point, move it to the left pi, so I'm there. And I can see my pattern at this point, so I'm just going to finish off my pattern. I'm going to start drawing along. I'm going here, then down, back up. Or I can just continue to move all of the points and then connect the dots. It's up to you. It's whatever your personal preference is. This is cosine of x plus pi. So those are our phase shifts. So fancy name, but it's still just left and right. So the next thing we can have is our period. And the period is just talking about the horizontal stretch and shrink. So the period is how wide each hill is going to be. So in our less mathematical explanation, it's how wide each hill is. And if we're looking at a picture of the period, I'm looking at my regular sine graph. The period is how long it takes the sine graph or the cosine graph to complete one full revolution around the unit circle. So the period is going to be from 0 to 2 pi. So it's one full pattern. It's one full pattern, so there's our period. Normal period is 2 pi. So normal period is 2 pi because that's how many times we're going around the unit circle. That's how long it takes us to go around the unit circle once. So period is 2 pi. If we're going to stretch or shrink the period, we can find the period or calculate it. Period will equal 2 pi divided by the b value. And the b value is right in place where our horizontal stretch or shrink would be. So our period is just our fancy way for saying horizontal stretch or shrink here, but because we're going to be stretching and shrinking every hill on the graph, then we want to talk about it as something that's happening multiple times, so we gave it a new name, call it the period. So our period is calculated by taking the b value and doing 2 pi divided by the b value. So let's look at some examples of this. If we wanted to find the period of the sine of 2x, so period equals, it's always going to be 2 pi divided by, and then I'm going to look at my graph, pick out my horizontal stretch or shrink, and that will be the number that I use in my denominator to divide. I get my period to be pi. So that means that now my entire pattern has to happen by the time I hit pi instead of happening by the time I hit 2 pi. So let's go in. Let's start by drawing our sine parent function. And again, I'm going to scale by 2's just so we have room to see what's happening here. When I scale by 2's, my sine parent function looks like this. At this point, you should be getting really good at drawing sine and cosine parent functions. Oop. And I noticed right away that I put 2 points in the wrong place because I was talking. Skipped one. So my sine graph looks like this. This is pi over 2, pi. This is 3 pi over 2, and 2 pi. So now, because we're talking about how long it took the graph to get to 2 pi, that entire pattern, that 0, 1, 0, -1, 0, now has to happen by the time we reach pi. So I can see that that means we're going to happen half as fast. So I'm still going to start here, but now when I start here, my next point will be here, 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 and here, because I needed to get this entire pattern to happen by pi. So everything's happening twice as fast as it was before. I'm just going to finish off my graph by repeating the pattern that I figured out. Everything happened 2 times as fast. So in the same time that I used to have 1 full period, so before my original graph I had 1 full period here, now I have 2 full periods because I have 2 full periods in the same amount of time. So that's a way I can check myself, is I want to have that many, however many, whatever my number is, my horizontal stretch or shrink, that should tell me how many periods I should have in the same amount of time that I had 1 in my parent function. So let's try with cosine. If we want to find the period, of cosine of 1/2 x, I'm going to take 2 pi and divide it by my horizontal stretch or shrink number, which in this case is 1/2. So divide by 1/2, which really means that I have 2 pi times 2 over 1, because I kept the top one, changed it, and flipped it, which says my period will now be 4 pi. So this means that I can get all the way to 4 pi, or I'm only going to have half of my graph in the time that I had my entire period last time. So this is going to take my graph and it's going to stretch it out. Count by 2's again, so I get pi over 2, pi, 3 pi over 2, and 2 pi. And again, I'm choosing to scale my x-axis this way because these are the 4 prettiest points on my unit circle. These are those nice pretty coordinates that are 0, 1, 0, -1. Those are those nice numbers. I'm intentionally omitting that √3 over 2, the √2 over 2. I don't want to deal with that. I want to deal with those nice pretty numbers, so that's why I'm picking these numbers for my scale of my x-axis. Okay, so if I draw in my cosine function, we know cosine starts at 1, 0, 1, pattern, just goes back and forth. Okay, this is my cosine graph. So now I need to take what happened in one period. So I can see one period of the cosine graph looks like this, because that's from 0 to 2 pi is one period. So I need that pattern to happen by 4 pi. So that means I'm only going to have half of what I had before. So everything is going to be stretched. It's going to be doubled. So all of those points that I had originally are now going to be twice as far apart. So if I stay at 0, I'm going to have my next point at pi, my next point at 2 pi, and it's going to take the graph and it's going to stretch it out significantly. So now, what originally was happening, what I was originally having happen by 2 pi has all the way until 4 pi, so I'm only going to see half of that pattern in the same amount of time. And then we have our last one is our vertical shift, which is just like our up and down. This is our up and down. Just like with our transformations, if it's positive, it's up, if it's negative, it's down. And the easiest way for us to do that is to look at this number that we add or subtract at the end, and that's how many our points are going to move up or going to move down. So if we look at the sine graph, I'm going to draw in my sine graph really quickly at this point because we know what it looks like. I'm also going back to scaling it by 1, scaling it by 2. Just stretched it out more. All right, so I have my sine. Oh, no, I don't. I have my cosine graph. And I know that because I started at 1. So let's finish drawing this. And then let's move these and switch them. That's my cosine graph. I need my sine graph. Back to the drawing board. Sine starts at the origin. Now I have my sine graph. And I'm going to take my sine graph, and this is telling me that I'm going to move up 1. So I'm physically going to take every single point and move them up 1. So I'm going to take this point, move it up 1. Take this point, move it up 1. Take this point, move it up 1. This one, up 1. And so on. Repeat my pattern so that I get a picture of my graph moved up 1. If I want to move down 2, do the same thing. I'm just going to take each point and move them down 2 now. So I'm going to take this point, go down 2, down 2, down 2. And so on. Finish off my pattern. When I'm graphing my trig functions, I'm using my knowledge of transformations, but now I just know that they have different fancy names for each of those transformations. So your classwork is going to ask you to pick out the values for the transformations, and then your homework is going to ask you to identify the transformed graphs.